Hello, my name is James Ryle. This is Physics 2211 Lab 5 Falling Motion. Overview. First, we're going to get into a brief introduction, followed by the physics involved in this lab. Then we'll look at the computational motion produced for the three objects tested in this lab. And then we'll compare these models and we'll produce some results. And then we'll look at some key takeaways and determine some answers for that. Introduction. Purpose. Computationally produce the motion of a series of objects of different mass dropped from rest. Compare the data from each of the models and determine if there is any difference. Results preview. In the data simulated by the computational models, all three objects had identical motion. This can be expected as mass is not a factor when solving the kinematic equations for time. Physics involved. Fundamental principles and equations. The important equations for this lab are F equals ma and F net equals the sum of all forces acting upon the system. In this lab, we are only accounting for the force of gravity on the Earth, as drag force will be negligent. The position update formula can be applied or can be both derived from Newton's second law. Computational motion. Gravity model. In this model, I took the equations provided before and I iterated through the falling motion of a object. For each model, I changed the mass of the ball. I kept the models at the same volume, and each model just had different densities as the masses of each ball was different. I set time to equal the total time between when it is dropped from rest to when it hits the ground, which was determined using the kinematic equations. Model comparison and results. Model comparison. The motion of the object at each mass is identical. This can be seen in the graphs as each model shows identical motion to the others. The range of the data of the graphs was shortened so that all negative values of height were excluded. So as you can see, each of these models appears to be equivalent. Results. All three computational models produce identical motion. This confirms that mass does not have an influence on the rate at which an object accelerates towards the Earth. The model did not consider drag forces, however, it can be expected these would not have an effect on the outcome because the objects were equal in volume. Key takeaways. What does it mean? What does this mean for the kinematic equations? This means that when manipulating the kinematic equations, students can gain an intuitive understanding of how these work in near-Earth settings. It is understood that objects of different mass will be accelerated towards the Earth due to the force of gravity at the same rate. What if? What if we had two objects of equal density but different volume? This is where the drag forces come into play. The object with greater volume and hence greater cross-sectional area will fall towards the Earth at a slower rate because it will encounter more air resistance. So a smaller object wouldn't have as much air resistance. So this can be thought of as a balloon moving through the air versus a bullet moving through the air. Now, while these objects obviously have different masses, you can think of it as the balloon is moving a bunch of different air particles out of the way, while as a bullet is slicing through the air and not moving very many air particles. This is why we ignored the drag forces in the previous part of the lab, because all objects have equal volume, so they will encounter the same drag forces. Thank you.